Okay, now let me introduce the speaker. Professor Landis is Professor Frank Taylor Professor of Civil Engineering at the University of Maine. His research interests are in experimental mechanics and fracture, with particular focus on innovative laboratory techniques to solve problems of damage in cement-based and wood-based composite materials. He also dabbles in computational modeling, biomimetics, burrowing marine invertebrates, and other things he should probably keep his nose out of. He has published over 100 scientific papers and is co-author of the text Fracture and Fatigue of Wood. Prior to his academic career, he spent several years in civil engineering consulting. At UMaine, he has been honored for both his teaching and research. In 2002, he was presented with the UMaine Presidential Outstanding Teaching Award. In 2004, he was the Distinguished Maine Professor. And in 2006, he was the Carnegie Foundation Professors of the Year in Maine. He has Bachelor of Science, a PhD degree in Civil Engineering, the Bachelor of Science from University of Wisconsin, and the PhD degrees from Northwestern University. And is also a licensed professional engineer in Maine. And today, he will talk about mass timber and the drive for better wood mechanics. Eric?
Wow, thank you, Gianluca. Of course, it's always nostalgic to return to Northwestern, even if it's virtual. Fun to see some of my professors, some of my teachers from when I was a student there. And so I appreciate the opportunity to tell you what we've been doing. And some of this involves work at Northwestern, which I'll go into. So I'm going to share my screen here, get started. So some of you may know when I was a PhD student at Northwestern and I got my start, I was really a concrete guy. But then when I moved to Maine, I would say I became a materials agnostic. You know, who knows what the right material is? So I've got a little bit involved with composite materials, FRP composite materials, and of course wood. And to this day, I'm still having a lot of fun working on all these different materials. Before I get started, a quick acknowledgement. Much of the research I'm going to talk about today is actually an NSF-sponsored a collaborative project with Professor Kusatis and his students. And my plan for today, first of all, in case you're not familiar with this term mass timber, I want to talk a little bit about mass timber, what it is, why it's gaining popularity as a structural material, and what new challenges it brings as a structural material. And then the last part, I'll talk about some of the work we're doing on this collaborative project where we're trying to address these new challenges. Now, before I get into the work, I do need to do a little plug for my my home institution. I'm part of a group called the Advanced Structures and Composites Center, and this is a fairly significant research unit under one roof, and it's a big roof, over 100,000 square feet. We can manufacture different materials, composite materials, wood composites, concrete composites, test them at a very small scale, atomic force microscope scale, and even a very large scale. And when I say large scale, I mean a very large scale. In our offshore wind lab, we're actually testing wind turbine blades that have been up to 60 meters long. So those are big structures. What's relevant today, what got us started in this laboratory is engineered wood composites. So we're doing a lot of work. We've got some active programs on a variety of wood composites, including what you're going to learn about is mass timber. So mass timber, if it's not a term you're familiar with, basically it's a new way of looking at how we build wooden structures. Most of you are probably familiar with, at least in the US, very common, probably most common for small buildings and houses, light frame where you have stud walls and then panel product, something like plywood or oriented strand board to provide shear resistance. But you're very limited in how high you can go with that kind of construction. Now with mass timber, you're actually taking dimension lumber, not unlike is in light frame, but now you're gluing it in together into big mass pieces. They could be panels, they can be walls, floors, and that opens the door to being able to build much taller structures, because now we have much greater structural capacity, particularly with respect to stiffness, which is usually the biggest drawback on wood for tall buildings. So the most common example of mass timber, well, the two most I would call are glue lam, which has been around for a long time. I would assume most of you have seen examples of that, where we just stack up dimensioned lumber, might be a 2x6s or 2x8s, into making a large beam. And the advantage of this kind of approach over, even if we had, well, the advantage is you don't need a big tree to make a big beam. But even if you did have a big tree, the advantage of this kind of approach is that you can grade each piece of lumber and you can put the best pieces of lumber in the places where you are likely to see the most stresses. So in a beam, you might put your best pieces of wood in the top and the bottom, and you can put all your junk in the center. Now with cross-laminated timber, it's a variation on that theme where we make up panels now. Instead of beams and columns, we're making panels with dimensioned lumber, but now we're gluing them together in different layers, where one layer will have the axis of the beams of the boards will go in one direction, another layer they'll go in the transverse direction. The principle is the same as plywood. If you're familiar with plywood, you have thin veneers that are stacked up in a way to give you some degree of transverse isotropy. In fact, I have heard people refer to cross-laminated timber as plywood on steroids. So these are engineered products. Again, we can build them to build the different elements to particular specification. And in using these, this is a very popular way to develop building construction in Europe. You have building companies that have what we might call Legos for grown-ups. You have a whole range of different elements that an architect and engineer can pick and choose to meet a particular design objective. Now, one of the points I want to make about mass timber is that there's really no such thing as a mass timber only building. We're almost always going to be integrating mass timber in with other materials. For example, this is a rendering of a building going up not so far from you in Milwaukee. It is a mixture of reinforced concrete at the lower levels and mass timber in the upper levels. And while this would not qualify as a super tall building, it certainly qualifies as a high rise. And I don't know about you, but that looks like could be a pretty nice place to live if you need to live in Milwaukee. Actually, I'm from Milwaukee, so I'm making fun of myself. All right. Some of you may be familiar with the Skidmore, Owings and Merrill project, where they took what for Skidmore, Owings and Merrill is a run-of-the-mill skyscraper and redesigned it with mass timber, looking at being sure that they could meet all of the required structural specifications, but then looking at the impact on overall carbon footprint. And what they find they had several different alternatives and now recognize, again, even a mass timber building will have some steel, concrete, and so forth. But they did find an overall reduction in the embodied CO2 of the high-rise buildings. And they could meet all the structural criteria. Now, why might somebody want to do this? Well, maybe you've heard of the term, you've certainly heard of conspicuous consumption. There's an alternative called conspicuous environmentalism. You know, the idea you want to drive a Prius to show how green you are. And some building owners may want to do the same, have these timber structures, because of course, this is a green material, it's renewable, and the wood actually is a carbon sink. So that's one reason for the rise in popularity. Now, again, if you're familiar at all with timber construction, the biggest challenge in building a large timber building is the connections. And so here's where different approaches are used for steel connections. This is actually a building that was built at the University of Massachusetts at Amherst, one of the bigger mass timber buildings in the US. And while the timber is the primary structural system, one problem with wood buildings, they tend to be loud. So in fact, for this particular structure, you'd see all these little pieces sticking out. That is to anchor in the concrete floor. So the concrete floor allows them to have a little bit quieter, more conventional building for the tenants. So with that introduction to mass timber, before I go to our specific research, I feel we probably need a brief review on wood as a structural material. Wood is very much a hierarchical material, not unlike concrete and some of the other materials you work with. We have a macrostructure scale with the features we can see with the unaided eye, a mesostructure, a microstructure, and in fact, if we need to, we can go down to the molecular level. The focus today will be primarily on mesostructural features and their role in structural performance, structural properties. So with that in mind, one more introduction is the coordinate system. I'm going to use quite a bit through the rest of the talk. Is we use a longitudinal axis for actually the axis of the log, and then a radial that extends from the center, a radial direction and the tangential direction. And the primary reason for establishing these is that those are the three principal directions that define different material properties. While if you have a board like this, you could approximate it as an orthotropic material, but it's not exactly because of the circular grain. Just a little bit of vocabulary. Get you up to speed, of course, is thing I want to point out here. Everybody sees the bark, and if you've ever peeled away bark, you get this kind of wet, slimy layer. That's the cambium. That is actually the only part of the what's referred to as the stem of the tree or the trunk of the tree. That's the only part that actually has living cells. So the tree, when it grows out, and actually it only grows out. In fact, I use what I call an engineer's tree view of tree growth, which shows this little sapling on the forest floor, and a tree grows up by growing out, is the way I would put it. So for example, if one were to put a nail in the side of the tree, that nail will never move up. It will stay exactly where it is, and the tree will grow up around it. And why this is significant for several reasons, but in fact, the structural properties of change as the tree grows. Towards the center, we have what we refer to as juvenile wood, and there the wood tends to be a little more compliant. because compliance is a little, it's better for resiliency if the tree can flex a bit. But of course, like with skyscrapers, as we get taller and taller, the wood needs to gain some stiffness. And in fact, the wood that's at the outer part of the stem tends to have better structural properties than in the interior. I'm not going to talk about this in our research, but in evaluating suitability of a particular piece of lumber, of course, knots are one of the key factors. And the knots are just discontinuities formed by branches. So if we have these little trees, as a little tree, it was growing branches, but eventually those branches get completely subsumed by the tree that's growing out. And then that gets what we get left with are these different knots. And sometimes the knots are continuous. They refer to that as a green knot because that's actually integral part of this of the wood. We refer to these as black knots or dead knots, where there's actually a literal discontinuity because the tree grew around a branch that was already existing. Another element that's worth noting is in wood macrostructure, the role of dimensional stability. So like concrete, but orders of magnitude more, wood shrinks and swells with changes in moisture content, but it does not shrink and swell the same in all directions. In the tangential direction, remember the tangential being along a growth ring, it shrinks in higher strain rate than in the radial direction. And that difference is why we get some types of warping within a board. If you have a board with a cross section like this, you're likely to get cupping because of this differential shrinkage. Now, the last structural issue I want to talk about is this cellular structure. Now, engineers' view of this wood mesostructure is, think of it as a bundle of straws. And this is more or less a very accurate way to represent the material, both from elastic properties, but also in failure properties. What do I have to do to fail the wood? We could just use this straw analogy. This shows X-ray CT images. Fortunately, I committed the cardinal sin of imaging, which is I did not put a scale bar. But these are on the order of maybe 20 to 50 microns across, depending on, they are definitely visible with the optical microscope. So the cellular structure, you have the cell wall, and then you have a hollow, what's referred to as a lumen. And the reason why this is important is that while wood has elastic properties, and for example, wood has a Poisson effect, but the Poisson effect is not like one you would see in a homogeneous continuum, because the Poisson effect is dictated not by the elastic properties of the continuum, but in fact by the structure, the cellular structure, and how the cells are arranged is going to dictate the elastic constants. And finally, I don't know if this is a universal feature of kids growing up, but when I was a kid and a tree got cut down in my neighborhood, I was always told, "Oh, Eric, count the rings." Because of what does the number of rings tell you? It tells you how old the tree is. And the reason we have rings, and this is, rings are more pronounced in temperate areas where we have more variation in season. But what the rings reflect is the fact that the tree does not grow at a constant rate through the year. In the spring and early summer, it grows very quickly. And then you get these very large cells with thin walls, and this is referred to as early wood. Then later in the year, that growth rate slows down, and then you get smaller cells, but cells that tend to have a thicker wall, and that we refer to as late wood. So early wood and late wood is what gives that ring structure. And this is important because you can just, even if you don't know anything about structural mechanics, one could probably look at these micrographs and say, well, if I've got a material of this section, that's going to be much stronger, much stiffer than a section cut out from the early wood. And of course, that is in fact true. We have to recognize this variation, especially, as I'll show later, when we're looking at the fracture characteristics. Now, this early wood, late wood, these rings can be quite pronounced. There's the image on the left, which indicates a sudden or kind of a definitive transition in growth rate, or in some species or some areas, you see a more gradual change in the growth rate going from these larger early wood to the smaller late wood cells. Okay, so that ends my primer on wood structure. So now returning to cross-laminated timber, CLT. And of course, we've been building wood structures for thousands of years. So despite the fact that the wood mechanics is quite complex, at least we know how to work with it, and we know how to work around some of the problems we have with the wood mechanics. However, up until cross-laminated timber, basically we were only worried about properties in the longitudinal direction, whether it's tension, compression, flexure, or shear in that plane in the longitudinal direction. But now with a cross-laminated timber, we're introducing a new stress state that we don't really work with a lot in wood, and that is shear in this, what I'll call the radial tangential plane. And so what we want to do is look at the fracture in this. So backing up, as a result, fracture properties of wood have been fairly well studied in the longitudinal and some variations of the longitudinal directions, basically crack growing in the longitudinal direction. Now we want to look at cracks growing in either the radial direction or the tangential direction. And that's the core of what I want to talk about with the rest of my talk. And put it in context, I just a little shout out to Gianluca and his team. So we have this collaborative project in which we are looking at fracture failure at a mesoscale, but we want to be able to understand that modeling at the micro and mesoscale in a way that then we can better predict properties of wood at the component and even structural scales, which is not a trivial problem. So what I'm going to talk about is some recent results we've had with small scale testing of fracture in this radial and tangential direction. So just one more primer. The notation used for wood fracture, we use a two-letter system where the first letter indicates the normal of the crack plane, and the second letter is the direction of crack growth. So in the case we're looking at today, we have RT and TR and some variations of the two. So in RT, the crack plane normal is the tangential direction, and the crack growth direction, the crack normal is in the radial direction, the crack growth is in the tangential direction. So I'm just going to generally call this transverse fracture. For these tests, basically we use, for something well known in fracture mechanics, a variation of a compact tension specimen. The species we're working with in wood, we always have to be concerned with that. We're actually using commercial lumber for this particular set of experiments in a species group called SPF, which is referred to as short for spruce pine fir. These three species are lumped together because they have fairly similar properties. And for this test, what we're trying to do best we can, and we realize we're not necessarily going to be successful, but best we can control crack propagation in a stable way. And thus we use a closed loop testing system that uses crack mouth opening displacement as the control mode. Then as part of the experimental system, we have a digital camera for measuring or monitoring the crack growth. And we use specimens for different specimens with different grain orientation. And the way we're defining the grain orientation is an angle alpha, which has this, basically it's the angle between the crack, the horizontal plane where we would define the horizontal plane of the crack, and the tangential direction. So if we have a alpha of 0, that means we are propagating a crack in the tangential direction. If we have an alpha of 90 degrees, the crack is going to be propagating in the radial direction. And our interest here is to measure crack resistance, but measure crack resistance with keeping in mind we have this variability between not only direction, but this early wood, late wood differences in material properties. So we want to measure crack resistance with an eye on the material morphology. So our experimental setup, we have a closed loop load frame with showing the digital camera with a microscope lens attached. Zooming in on the specimen. Now this is going to be a specimen with an angle, alpha angle close to 90 degrees because the crack plane is the radial direction, but the alpha is pointed in the tangential direction. And here's a clip gauge to monitor crack mouth opening displacement. And as I said, for most of the tests, not all of the tests, but most of the tests, we use the feedback, the output from the CMOD gauge to control the test under a closed loop system. So a typical result for, or a typical analysis, this shows a load CMOD curve, very characteristic with the linear pre-peak, and in this case, relatively stable post-peak. And while this test is taking place, we're taking photographs, taking digital pictures. And so these marks measure where we have photographs. And from those photographs, or I really should call it digital images, we can measure crack length. So as the CMOD grows, as does the crack length. Now for our crack resistance, we're interested in just best we can incremental crack resistance. So over a range between say two different points, in this case between 0.2 and 3, we will measure the change in the dissipated energy, and then the corresponding crack growth over that range. And we just say that the crack resistance is simply the energy divided by the crack growth, the crack area, which is the crack length times the specimen thickness. So the first result I'll show is angle of 0. So now the crack is propagating in the radial direction. And again, what we see is relatively stable crack growth, both are fairly stable descent in the load CMOD curve, and a relatively straight crack growth. Now we do see some fair amount of variability in this, in the crack resistance as the crack grows, although we're not necessarily seeing anything that would resemble a rise or a fall. We wouldn't necessarily call it a rising R curve or dropping. Now let's compare this to what we see in the images. So we've got, say, the crack growth from 1 to 2. What I failed to mention before is we just like in a regular compact tension test, we prime the crack a little bit. We cut it with a little razor, get this crack growing, it started. Then as it goes, what you see the crack grow, it simply follows the early wood. So not necessarily obvious from the image, but you definitely see the early wood, late wood sections. In this image, the light areas are the early wood, the late wood, the darker sections are the early wood. And this is exactly what we would expect, that we have these thin cell walls, bigger cells. We would expect that to be the path of least resistance. So now if we turn the specimen, now this angle is 37 degrees. We see some instabilities in crack growth, at least initially relatively constant resistance. Let's see how that compares with how the cracks grow. Well, unfortunately, the cracks grew right through our label, but here again, crack simply propagates along the this early wood region. Now, of course, fracture theory tells us that at least if this were a homogeneous elastic material, to maximize strain energy release rate, we'd want to go straight. But because of this lower resistance, the crack curves. Now, an interesting thing starts to happen just a few degrees more. Again, we see some instabilities, but otherwise stable crack growth. But now in this case, looking at the cracks, we see the crack wanting to go follow that early wood path, but the angle is steep enough that we start to cross over the late wood, which means we've got to break through what would seemingly be a stronger section of the material. Then we do have a gap, I admit, but now they go to an even steeper grain angle. And now what we see, definite regions of crack instability. Despite the fact that we have CMOD control, you can picture if a crack is going from a region of higher resistance to lower resistance, once it gets through the high resistance, it's probably going to have enough energy to propagate through. Now, what we found of interest here is now the early wood, late wood orientation is, again, it's 60 degrees relative to the initial crack. But if you look closely, it's a little hard to see because we're seeing artifacts of the saw cut. The rings are in this direction, and see the crack, it just turned and goes normal to the rings, which is directly in the radial direction. So this implies now that the radial direction has less resistance, even than going straight. And then finally, if we go to 90 degrees, now this is what's referred to as TR again. Now it's definite sections of unstable crack growth. And if we look at the images of the crack growth, again, it's the saw artifacts might be showing up here, but the grain of the wood is vertical here, and the crack simply propagates straight across with very little resistance, and basically no toughening. Now, something I want to point out for those of you who are experimentalists and spend a lot of time in the lab, sometimes you look at these curves over and over again, and you just can't help but see certain things. In this particular example, we just could not see Maine was hiding in that little region there. So this particular failure mode became the main failure pattern. For those of you who are not familiar with this is my home state. All right, so some observations summing up what we've seen. So alpha equals 0. So this is, now we're propagating a crack in the tangential direction. Basically, the crack stays in the early wood, and we have very stable crack growth. We have a high variability in crack resistance, but we don't really see any toughening. We increase that angle, and now we start to see some instabilities. but still the crack stays in that early wood, propagates along in that tangential plane. But at some point we see a transition where now the crack wants to maximize energy release rate, so it starts to migrate through the late wood. And as we get even higher alpha, now we start to follow the radial direction, and that is accompanied by local crack growth instabilities. And finally, when we go in the purely radial, the crack is going in the purely radial direction, we have locally unstable crack growth, and the crack will just propagate in that radial direction, which suggests that, in fact, the radial direction of crack growth has lower overall fracture toughness than the tangential. And to test this in another way, we took our data and then, dusting off my fracture mechanics of concrete, we just looked at overall fracture energy. So we take the energy, we basically load the specimen out as far as we can, get the area under the curve, and divide that by the change in crack area. And plot that for different different angles. And of course, statistical significance may be a problem, but the trend we want to see, or that we see, whether we want to see it or not, we get an increase and then a decrease. So in fact, the radial direction, which is represented out here, is lower. And I want to emphasize that at 90 degrees, remember, we had all of this unstable crack growth. So in fact, we have no way to properly measure the energy dissipated because of the instabilities. So therefore, these values out at 90 degrees we can say fairly conclusively that is an overestimate of fracture energy. So what next? So what we're very interested in, I mentioned that we're interested in the morphology and the localized failure mechanisms as a what aspects of the wood are we failing? And so what we've got going on right now are some acoustic emission tests that we hope will allow us to distinguish things like where we're rupturing the cell wall of the wood as opposed to just separating the fiber, pulling the fibers apart, because these wood fibers are discrete. And once we're comfortable with that, we will return to some earlier tests. I mentioned this term rolling shear. Well, this is a way to test it. We just have a compression test where we create a shear plane in the direction that is going to induce failure. Whoops, I ignored the subs parts there. And then for my friends at Northwestern, we want to put everything in a form that's useful for computational modeling, because we want to be able to appropriately predict performance at a component scale or even a large scale CLT materials. So to summarize, hopefully, you've seen mass timber as a structural material that's gaining popularity globally. I didn't really mention this early on. It's already quite popular in Europe. It's only gradually gaining popularity in North America. I do want to emphasize there is no such thing as a mass timber only building. We're going to need different materials to, particularly for connections and other structural aspects. But I mentioned the CLT products open mechanics questions because we're loading the material in ways we haven't before. And hopefully our new data on fracture will help drive model development that ultimately can speed development of new ways to utilize mass timber, which is really the end game here. And with that, I will end my presentation. And this is roughly what it looks like outside my window today, although not so many students. Thank you for your attention.
Thank you, Eric. It was excellent. Thank you. Let's unmute and clap. Let's hear that you guys are there.
Thank you.
Excellent. Okay, so now the questions.
I have one.
I have one.
Yes, go
Um,
ahead, I say first.
so as you mentioned, one of the issues with the compact fracture testing is an inability to very accurately test, especially at that 90 degrees with all that instability, the energy released. And you mentioned using acoustic testing, hopefully to give more insight into what is actually happening. Does that acoustic testing also allow for a more accurate, would you be able to do similar angle-based testing to get more accurate insight onto what's happening across angles? And if not, what would be a test which would allow that?
Yeah, so the acoustic emission will not tell us anything about the instability. And now I say not possible to test stably. I should qualify that, say I was not able, myself and my student were not able to test, come up with a stable crack condition. And I feel like I learned how to do this from some pretty good people, some of whom are here. But I think because of this variability in early wood, late wood, I'm not sure it's a possibility without some really innovative way to control, that you're at a much more sensitive approach. No, the acoustic emission, what that is, we know that there are different failure modes at the microstructural and mesostructural level. I mentioned in a shear failure, like in a rolling shear failure, you might get fibers separating, just pulling apart, but you also could get the tearing of the cell wall. And we're interested in knowing that difference because that might help us be able to predict, based on simply the early wood, late wood characteristics, what kind of failure we're likely to get, and then use that information accordingly. So the acoustic emission is really just, it's not to help us get information about what we're missing due to instability. It's just to get us microscopic failure modes.
Great. And I also want to just give a shout out to Peng Shen in the comments for an excellent pun on your main comment. Professor Bajaj.
That is one of the challenges of a remote seminar is, I can't tell if people got the joke or not.
Oh, Eric, I have a question.
Okay, Suru, I think Zdenek was before, then you go. And then
Sorry, go ahead.
Yeah, Zdenek and then Suru.
I have actually 3 questions, but quickly. You showed this diagram of low deflection curve and gradual softening, and then you showed unloading curves.
Yeah.
A straight line shooting to the origin. That's that must be assumed, because for no material it is like that. In fact, in concrete, the unloading goes much more steeply. And in fact, we studied in the 1990s, and we estimated that about 60 or 70% fractures in concrete is due to friction, plasticity. And actual microfracturing is only the rest. So that's one point.
Yeah. So a good point. Yes, you're absolutely right. The straight line back was assumed. I mean, we do have an unloading, so we could use that. It was just for simplicity. And you bring a good point. We need to calculate it both ways to make sure that we're not missing something. I think what's different in wood than concrete, though, is that while I'm sure there's some frictional effects, because remember, this is a cellular structure, and you're only having material connections at discrete points as the crack grows. So yes, there certainly can be some friction, but I don't think that friction is very much in the unless we have one of these cases where the crack is, say,
friction
curving.
and plasticity, because
I'm sorry?
friction and plasticity.
Plasticity, yes. Yeah, that could
But
be.
it actually is, hard to distinguish which is what,
Yeah.
right? Because you would have to know the normal stresses.
Yeah.
But the unloading doesn't go to origin, but also subsequently at the next point doesn't go to the same point. And from the distance between this point and the basis, you can distinguish what is plasticity, what is fracture. Because it can be decomposed in two steps, plastic and horizontal and fracture. Well, and that actually gives a split between understanding the fracture energy. The other point I just want to mention, we just recently so happened we studied sideway cracks. And we found that they have a stronger side effect in composites, not in wood, in autotropic composites. They happen only at a certain degree of autotropy, otherwise they don't. Probably that's the case of wood. So that's one interesting point. And the last point I wanted to mention: are you measuring if trying to determine which of the fracture process zone? You can probably get it from acoustic emissions somewhat. That's very
Perhaps.
for crack parallel stresses.
Yeah. Our assumption, so there's definitely a fracture process zone in wood when the crack propagation is in the longitudinal direction. So one of these LR or because you get a lot of bridging effects.
You mean width, wide zone?
Well, we see a lot of bridging because fibers actually.
Okay. All right. Okay.
You know, we do see some crack. You know, very similar to concrete. We see micro cracking. We see bridging. Yeah, we're for the short term we're punting on or kicking the size effect down the road in this fracture, and our justification is because we're not seeing any continuous. We don't see a rising R curve. It tends to be fairly constant. Now, maybe that just means the process zone is small and moves with the material. Yeah, for the time being, we're using the fact that we have a constant R, more or less constant R curve to punt on the size effects.
Probably look at too, the effect of crack parallel stress would probably be very big, but not in the fracture. It's just a line.
Okay, very good.
That's it.
Suru.
Great seminar.
Thank you.
Very nice presentation.
Yeah, good. I'm confused with your term early wood and late wood because the rings are all chronologically. So
yeah. So early wood refers to early in the. It was wood that was cells that were formed early in the year, early in the growth season.
Okay.
And late wood is the cells that formed late in the growing season.
So for each ring, you have early and late.
Correct. So if you go down to the microscopic level, each ring is going to have many layers of cells.
Yeah. Very good. Thank you.
Any other question?
Eric, I had a similar question about early wood and late wood. In the micrograph you showed I think it kind of showed 2 years, and one of them there was a lot of late wood, and then in the next ring there was a very small amount of late wood. Is that just variations in the growing season that year, or?
It is, and in fact, interestingly, archaeologists are using that. It's a term called dendrochronology, where you can take a very old tree, something like a sequoia, pull out, drill, core out, and you can basically reconstruct the weather weathers. We'll call it climate. So yeah, that's that can be very useful. Not so necessarily useful for structural applications, other than, I like to tell the students that 150 years ago, Maine had some of the most desirable lumber in the world, because you had these very old, tall, straight grained, and the trees grew very slowly, which means the proportion of late wood is greater than early wood. So slow growing trees tend to be better structurally than fast growing trees.
Right.
So
And the other thing that popped into my mind is since there's such a variation in what you get depending on the conditions, do people try to alter the conditions or somehow force the tree to grow more old growth or old wood?
yeah. Short answer, I don't know. That's a forestry question.
Yeah.
My suspicion though is that generally, especially in the South, like in Georgia, and they have southern pine plantations, and I think they're trying to grow them as quickly as they can.
Yeah.
I mean, one of the fun facts about wood is that in the U.S. right now, there is more available wood resource today than there was 50 years or even more 50 years ago. However, the quality of the wood resource continues to go down because, for example, in Maine, you have these magnificent virgin forests that became ship masts, spars, and keels. And now what's replaced it is, it's pretty junky. I mean, it's really good for paper, so which explains one of our chief industries in Maine. It's not as good as a structural material, which is why the rise in the use of engineered wood composites as opposed to just solid lumber.
Great. Thank you very much, Eric. Great presentation.
Anybody else? Somebody from the student audience?
In terms of,
I have one brief question.
I think it was Raul first, and then Jibril. Yes.
In terms of the cross-laminated timber, is there any study of the adhesive, like interaction, how the adhesive between the laminates is transferring the loads between them, or if there is a failure on that plane? And
yeah, absolutely. Because of this engineered wood composites have been around a long time, the glulam, but even something like plywood, and so adhesives properties with wood are pretty well known. In general, the adhesive is stronger than the wood. So, so if you fracture the material at the bond line, you typically get failure of the wood, not the adhesive.
Okay.
But of course, that assumes that you apply everything properly and so forth.
Yeah.
Jibril.
Thank you very much for the presentation first. I would like to ask about the crack experiment. Have you observed any crack branching, or is the ring structure preventing this?
Yeah, it's a good question. Occasionally we do see crack branching, although usually what it is a crack forms and then kind of stalls and another one takes its place. So it's not quite the same as crack branching, but it's, and I will say something I should have mentioned, there is a limitation in our crack measurement, which is going to put a lot of variability in our measurements because we're only seeing one side of the specimen during the test. At the end of the test, we can look at both sides and see how long the crack is. But during the test, we only have the capability to watch one side at a time. And what we have seen on occasion, we'll say, wow, a crack started here and then it stopped, but then another one went in another location. Well, then after the test, wow, we can't explain that. Well, we turn over the specimen and we see on the other side of the specimen, it was the exact behavior we normally observe. So the fact that the crack is not always, that there are three-dimensional effects in the crack growth, to be sure. And I didn't go into detail, but the variability in crack resistance in R that we see, even when the crack propagates through this early wood zone, often we'll see these little localized, jumps, even within the ring, but then that little jump will correspond to a little rise in R. So there are some fairly small features that we can trace, the variation in crack resistance to those features. And in fact, that's what interests us the most.
So maybe the last question from the chat, I think it's well, probably we don't have much lot of time to answer, but he's from Peng Shen, and he's asking, I'm wondering how has your education background, Northwestern particularly, I add, and early career choices prepare you for your career today? And if you could give advice to your undergraduate graduate school self, what would it be?
Yeah, that easy. Be open-minded about opportunities. When my return to grad school to Northwestern, interestingly enough, I wanted to work for Skidmore, Owings and Merrill, and I knew I had to get a master's degree to do that. So when I originally went back to Northwestern, it was just for a master's degree. But then took these classes that I enjoyed, and I did a little TA work to earn a little extra money, and then Professor Shaw had this little fellowship for me, but only if I would stay for a PhD. And thought, well, that's a really great opportunity.
And you said yes, thinking that then you would leave anyway, but then you stayed.
I said yes, actually, not having the confidence that I could do it. I did not have the most stellar undergraduate academic record, so it was a bit of a stretch to think that I could get a PhD, but maybe that's my example, that you don't actually have to be that smart to get a PhD.
Oh, you do, especially at Northwestern.
So anyway, yes, Northwestern was, of course, a fabulous opportunities, and yeah, my career advice is be open-minded about opportunities, and yeah, that's I can't imagine doing anything differently now. I have the best job in the world.
Okay,
and
thank you.
I meet all these really interesting people from all over the world. Nice perk.
Thank you very much, Eric. Thank you. Let's
All right, very good. Thank you. Fun.
Okay, this concludes our seminar today. Thank you, everybody. Bye-bye.
Thank you.
Bye, everyone.